Okay, so we have turned in the homework assignment and turned back, returned the previous assignment back to you. Today we're going to continue a concept called memory mapping. So we're going to go into the basics of cache, how you talk between levels of cache. In section 7, we're going to be going into a lot more detail on a concept called cache coherence and cache consistency, especially in multiprocessors. That's where it becomes very valuable. But in the meantime, I want you to understand like the concept of a tag, an index, block, how you use this byte addressing, how you're actually trading pieces of memory in between levels of cache. And we're going to talk about two concepts called direct associativity and set associativity, and how that's actually used. So you have these lower levels of cache which have a certain amount of memory, right? And so as the levels grow, we need to still maintain some sort of addressing. So if you think of it kind of like a street, like you have a certain address that you're going to, and let's say each house on the street maps by like 1,000, so 1,000, 2,000, 3,000, 4,000, and then those are blocks, and those break down into, they count up to 10, so 1,100, 1,200. You would actually know, okay, so if I know I have to go to 8120, I go to block 8, and then I go to house 6. So if we're counting up by 20, that gets us to 8120. So the whole idea is, how do we actually map this information to different levels of cache? So the first thing is what I just described. TGO 5.13 is the definition of an index. An index is the numerical value used to indicate the exact location in the cache. Very simple. It's right here. So if I have 8 words of memory, right? 32 bytes. And I have 8 elements in there, then I have, how many bits would I need to represent the index? How many bits do I need to represent the index? So I have 8 locations, right? So why 4? 8. So I have 8. So I need to count from 0 to 7, right? Mm-hmm. So what's 3 bits? Is what? 111 is 7, right? So in computers we start at 0, so you go 0, 1, 2, 3, 4, 5, 6, 7. So how many bits do we need? 3. Correct. So that's the index. The index tells me where I'm at. So to tag, so here's the thing. If I have 8 blocks, and then I have to map, I'm at a 32-bit level, and then I have to swap those out, 8-word blocks. I need to say, if we're breaking it down, where's my chalk? So I have 32 bits, and I'll show you a figure later. 32 words, 1, 2, 3, 4, 5, right? And then the lower level just has one 8-bit, right? Sorry, 8 words. So you're 0, 0, 0 through 1, 1, 1. And then I want to be able to perform swaps where, remember our block from the earlier definition is the smallest amount of information we could swap between the levels of cache. So how do you think I would actually address this level? If I have 32 words, how many bits do I need? Kind of from 0 to 31. 5, right? So this goes 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, right? So if I'm going to swap any element from here to here, which portion of this address do you think would map to the index here? No idea. Let's go back to the analogy of blocks, right? So we're on a street block, right? So I know 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. That initial one, right, tells me where my block is, right? So if I'm breaking into 5 blocks, how do I know which block I'm in?
Most significant bit.
What's that?
I said the most significant bit.
Most significant bits here, right? We actually have 5 blocks we're going to count up there. So we have 8 right? So we're going to be counting 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, right? 1, 2, 3. Yeah. We need 3. And then from there, each one of these is going to contain 8 blocks, right? Actually, I said 40 instead of 32. So let's get rid of this. So this is now 32. So now this is 0, 0, 0, 1, 1, 0, and 1, 1. Right? So we have 4 blocks, 32, right? So now, these other, so the 3 least significant bits are going to match our index. Does that make sense? So every single block, once you take out that first number, so if we have 7,000 and 8,000, you take that off, and if you have 1, 2, 0, 1, 2, 0, 1, 2, 0, so 6, 1, 2, 0, 7, 1, 2, 0, 8, 1, 2, 0, you know that 1, 2, 0 for breaking the 20-bit, 20, right? That's the 6th house in the block. So, you know, like I need to go to the 7th block and then the 6th house, or the 3rd block and the 4th house. Here, I know if I have 0, 1, 1, 0, 1, I know that I need to go to 0, 0, 0, 1. So I go to the 2nd block, right? And then I go to the 5th word in that block.
6.
4 plus 1 is 5.
That's 5, but it starts at 0.
Okay. That's number 5. 0, 5, 6, whatever. You are correct. Analogies. Okay, so you see what I'm saying now? Alright. So the key thing is now we have to perform swaps. This is where our faster level of cache is. And then we have to swap that information out. So our tag indicates which element is currently in the hierarchy. But here's the thing. We want to have the 8. So they're breaking this into 8, right? If I'm using 0, 0, 1, 0, 1, and then here I have 0, 1, 1, 1, 0, I can't, anytime I want to switch any element in the blocks with the specific index, I have to swap that word out, correct? So what we're going to do, that's how we perform this mapping. So what we're going to see in this diagram, I'll show you in a little bit, is that every single one will map to the same element in the lower level of cache. And that's where you perform your swaps. So the index for each of those is going to, they're all of the same index value in each block is going to be mapped to the same element. This is called directly mapped cache. So directly mapped cache is a cache structure in which each cache is mapped directly to exactly one location in the main memory. And so you guys have already derived these two equations by coming up with the number of bits that you need. So the size of the tag is log 2 of memory divided by block, and the size of the index is log 2 of the block. So log 2 means, like I told you, there are 8 elements in the block, right? So log 2 of 8 is 3, right? Log 2 of 32 divided by 8, that's 4. So log 2 of 4 is what? 2, correct. So there you go. So now that's how you come up with 2 and 3, just like we did here. So these are the formal equations to define those. So the figure below, this kind of figure that I've been alluding to, is actually going to show you kind of, this is the exact example we came up with. So we have 8 blocks, 32 divided by 8, 5 minus 3 is 2, right? And the same thing, log 2 of 8 is 3. So this is it. So here, these memory elements, these values, this is the index, right? The 0, 0, 0 through 1, 1, 1, right? You can see how each of these, so all of the ones that are in orange have the same index of 1, 0, 1, right? So if I initially load 0, 1, 1, 0, 1, into this lower level of cache, that's the element that's going to be in the lower level here. So then what happens is, let's say I perform a memory load operation where I need this value 10101. So here's what's going to happen. If this value is currently in the memory, and this value is the one I need, what I'm going to do is I'm going to swap this element out, put it back into the higher level of memory, then I'm going to take this element and put it in. And that's how directly mapped cache works. Does that make sense? And if we recall, this level of cache is going to be higher than this level of cache. So this is kind of exactly how a load and store operation works. If I have a specific, the compiler is going to say it's going to take advantage of that principle of locality, take advantage of that temporal and spatial locality. Elements that tend to be used will be reused again. So we're going to want elements that are going to be reused often in these lower levels until we absolutely have to swap it out. And from there, all of these blocks in here, that's where you take advantage of that temporal locality. And if you recall from earlier, we were talking about how the lower levels are cheaper but run slower. So that's where this lower level is faster but more expensive. This higher level is you go up level 1, level 2, level 3. There's more memory, but it's slower. So we want to put the elements we're accessing faster in these other levels. So this example question kind of gives you an idea of how to determine precisely how big your tag and index and your memory needs to be. So we have a block is 1 byte. Memory is 16 kilobytes and a cache of 256 bytes. Determine the length of the index and tag of a directly mapped cache. So this memory is 16 kilobytes. That translates to 16,384. When you hear 16 kilobytes, that's what that number means. What is it in, what do you think 64K is? So let's do a quick thing. So 2 to the 14, right, is 16K, right? So how do we represent 32K? What's 16 times 2? 32, right? And if I multiplied this side by 2, then I would multiply this side by 2. 2 to the 15, right? Likewise, 64K becomes 2 to the 16. And what's the exact value of 2 to the 16? I'll give you a hint. It does in fact start with a 6. 65,536 is the exact number. So 64K is actually 65,536. So the numbers are not numbers. So that's the reason why I specifically stated this out. 16,384. When I say a memory of 16 kilobytes, and you're in industry, and you say that's exactly 16,000, people will look at you funny. Yeah, don't be like creepy Rob Lowe. Be like regular Rob Lowe, I guess. And now I know who watches football. Okay, so now we use the same equation here. We find the size of the index. We know that our cache is 256 bytes, right? So we have log 2 of 256 is 8. Eraser anywhere?
Yeah, it's right behind that. Right behind it.
Oh, there it is. So a simple way to figure this out, I mean, you will have calculators available to you on the exam, but log base 2 of 256 equals x. What this actually means is you start at the base of that, you come around, and you follow like that. So that means for like 2 to the x equals 256. So that means, in this case, x equals 8. That means we need 8 bits to represent an index. So if we have 256, going back up to this one, instead of having 8, we have 256 here. And then here we have 2 to the 14 divided by 2 to the 8. And the reason why it's divided by 2 to the 8 is because of the number of the repetition. That's what we derived for. So the simple way to do it is if you have 2 to the 14 divided by 2 to the 8, remember, if you have this inside the logarithm, it's the same thing as just taking the powers and subtracting them outside. So that becomes 14/8 minus 6. So then your tag is going to be 6 bits because you're going to have, you need 6, 2 to the 6 representation to be able to represent all the different potential elements that can be in one index in the lower level. The index itself needs 8 bits because you have 256 bytes. 256 bytes. And here I say memory is 8 bits, and the reason why is because a block is 1 byte. So here we have an 8-bit representation. So this is, if you had a cache, if you were required to build a cache in your data memory, this is where you would start.
So in those equations where you say log base 2 of block and log base 2 memory of a block, block is the number of blocks in the cache, and memory is the number of blocks in the memory.
Correct.
Okay, that confused me.
Okay. So here, if I'm wording the question, you have, this is the lower level, and this is the higher level. So this problem, 256 represented this, and 16K represented the memory. So take the analogy back to the streets. We have 6 blocks, meaning that we start at 0 and then we go to 1 and 2 and 3 and 4 and 5 and 6, and then each house, and then each block you need 8 bits. Right? So it goes from 0 to 255. And what does that sound familiar? What else do we need to, something earlier in the course, what do we need 8 bits to represent? I'll give you a hint, you might see it on Thursday. You need 8 bits to represent what in IEEE, what? Ah, yes. Yes, there you go. Not the mantissa. The mantissa is 23 bits, but the, what's the other thing? You have the sign bit, you have the mantissa, and the thing I'm looking for. The exponent. The exponent, you need 8 bits, so you need a 255. So, friendly reminder that you have an exam on Thursday. Okay, so now we're going to be going into an example here of how we're actually performing these swaps and what's actually going to happen. So we are given a direct map cache, just like we've described before, with 8 words, and the address reference is 22, 26, 22, 26, 16, 3, 16, and 18. Show the sequence for accessing the cache, and assume the cache is initialized as empty. So what this means is we're going to be breaking these values into binary, and we are going to be saying, with our knowledge, all right, we have 8 words, meaning that we need to break this index into 8. So if I have 8, using our equation, that's log 2 of 8, which is what? 3. Good. And then I have a valid bit. Now the valid bit here is V with all n's in the first table, indicates that there's nothing in the memory, which is how, when I say assume the cache is initialized as empty, that's what that means. So right now we have nothing in the memory. So for this first step, the first access is 22. So 22 is 10110 in binary. we know that the three of these significant bits are going to be the index. So if you look over here, we go to the index 110. We change the valid bit from no to yes. Now we have something in there. The tag is going to be 10 because those are the most significant bits here, right? And then the index is 110, so that's the least significant bit. So we just load it in there. Now, this is what is known as a cache miss. Remember we were talking about cache hits and cache misses last lecture? The reason why this is a cache miss is because it wasn't there, right? So if we look for it, it's not there, we have to go to the higher level of memory, right? Which is what we did. We had to go to the higher level of memory, and now we're physically putting it in the cache. So this is an example of an initial blank cache miss. So now we go to 26. That's our second one. So that's 11010. So we go to step 3 here, and we change the valid bit from no to yes. The two most significant bits are 11, so that's going to be our tag. And then 010 is going to be our index. So we go to 010, we see nothing's there, we put it in memory. So the way this breaks down is 11010, valid bit is now yes, and the data is now the actual representation. So that memory right there, that's what's actually we physically need. Now, step 3, so initialize 0. Step 1, we have a miss. Step 2, 26 is a miss. Step 3, the next one is 22 again, right? So we go to 22. We look in that level of cache. Do we have it? 10110. That is precisely what we have. So that's a hit. So instead of having to go to the main memory and perform a swap to bring it in, we just grab it from that level of cache and put it into the registers, right? So that is what a cache hit physically is. And then step 4, 26. 26 is already in there, right? So guess what? We have another hit. We don't have to worry about anything. Step 5 is 16, and it's a miss because we break 16 is 10000. So what's our tag in 16? 10. And what's our index? 0. Yeah. I saw one person go 000 with their hands. And so we find the index and we put it, nothing's in there, so it's a miss. So we load it. And so here's the step 7. We have 16. Now we have 3. 010, 011, right? So you have 00, 011. We load it in. And then 16 is a hit. Now 18 is 10010. So you notice how 18 matches 26 in terms of the index? So what do you think we have to do? Swap it, right? So now we're going to take 26 out of the cache and we're going to put 18 in. So we had 3 is a miss, 16 is a hit because we already have it in there, and 18 is a miss, and then we have to perform a swap. So you see 26 for 18, 010. We now have 10010, which is going to be 18. So this is what the cache in a directly mapped cache looks like. I'm sorry, let me scroll up to the solution here for you. This is what I need to see on an exam. People come up with all kinds of different and interesting ways to. Some people will write out. They'll have a little table on the side, and then they'll write the final table, which shows the final solution. And they'll have step-by-steps to break things down, or they'll actually. It's awfully time-consuming to draw out each table like that. So But as long as you can get to this solution, but do you see how it's kind of, once you understand how a tag works and how an index works, that they kind of just break down, and it's actually, a fairly straightforward problem, right? Yes, no. A couple of people going. Does anybody have any questions on this before we go to set associativity?
What'd you do whenever you got a miss? Like step across the 16 miss?
Right. Well, we're going to be going, the last example, we're going to be, so if you had a miss, you would actually, remember how last class we did average memory access time? Basically, so you have that level where if you're not there, then I go to him, and then they swap the information. And if you're not there, I go to INSO and so forth. So that's what's actually going on here. You have a miss. If it's not there, you actually need to go to the next level and say, hey, I need this information from you.
How did you know you had a miss in this problem?
Okay, so first step, everything's empty, right?
Mm-hmm.
So we have no information.
Yeah.
Step one, we look there. Is 22 here? Mm-hmm. If it's not there, that's when we have a miss.
Oh, okay.
So that's what the first thing we do is we look for the valid bit. Oh, no valid bit, then we don't need to check the tag or index. But then we change the valid bit, so then we would say later when we do 22 hit here, we would go to the tag, we would go to the index and say, okay, is there something in the index? Yes. If there is, we then check the tag. If the tag matches, that means it's a cache hit.
Yeah. Okay.
And so forth. So we actually had 22 hit, we had 26 hit here. 16 was a miss because it's empty.
Yeah.
And then 7, 8, 9, I kind of simplified for space, but 7 was 3, so it's 0, 0, 0, 1, 1. 8 was 16, which is a hit because we already have it there. And then 9 is a miss, and this is the important part. Let me scroll back up so people in the back can see. So in the previous step, we had 22 here, right? I'm sorry, we had 18, so that's, so you had 1, 1, 0, 1, 0, right? So that's not 18, but we do have a valid bit, so then we have to perform a swap of the most recently used value in the cache. Any other questions? All right. So set associativity. So now in this previous example, let me get my chalk here. So in this previous example, we had just one block of lower level cache. We were going to call this, now let's say instead of having our index, we can make the index smaller, but we can actually have two streets. So street 1 and street 2. In this case, we're just putting everybody in the neighborhood on the same road, because it's a long road. But let's say we want to create a second road, or a third road, or a fourth road. So that way, you can go, I can turn down the first road, I can turn down the second road, then go to the second block, fourth times, right? In cache, this is what's known as sets. So think of different roads as different sets. So if we wanted to have 8 elements in the cache, but if we want to have 2 sets, we would just break it down into 2 sets of 4. And so what ends up happening is we actually allow for multiple instances where 0, 0, 0, 1, 1, 0, and 1, 1. So that's set 1, or set 0, and then 0, 0, 0, 1, 1, 0, and 1, 1. And so we have that same tag. So in that previous problem, remember that, was it 26 and 18 swap that we had to perform? Well, we would look here, we would see 26, and they go, okay, well, 26 here, but then we check the second set, and we just put 18 there, or write the way humans read it, 18. So that means instead of having to perform a second swap, we would just load it into that other set, and that allows us to actually produce. This actually ends up being more efficient. Okay, so 5.7 is an example. So let me read the definition. So it says set associative cache is a cache structure that has a fixed number of locations where each block can be placed. And an n-way set associative cache has n locations for a block. Think of it as a direct map cache. Yeah, so direct map cache is a one-way set associative. So back to our analogy, one road, direct map. Two roads, two-way set associative. Three roads, three-way set associative. So the way we'd set it up, so we have 5.7, so we have the exact same hits here. So again, we break it down, but now we have a two-way set associative cache. So instead of having an eight blocks in one row, we would have our tag is going to be, our index is going to be 2 bits. So it's going to be the normal index divided by the set, the n-way set associativity. So if we had 4, so let's say we made it a 4-way set associative, then everything would just be its own road. Everybody would have its own street. And here, this just makes it more efficient. So we initially start out, everything's empty. We put in 22. We look at 1, 0, right? And then we're going to look at the first 1, 0. Now we have 2 blocks that they can be put in. So we put 22 in here. And we go, is it there? No, it's initially a miss. So we put it in this first set. 26, we have 1, 0 again. So that matches 22. In the previous example, in direct set associativity, we have to swap it out. But then we just put 26 in the second step. And then our next two are 22 and 26. Hit, hit.
But it'll still be a miss if you didn't find 26 and either one of them, right?
Right. Well, if you didn't find it. But so the initial, so 22 was a miss, the initial 22. The first 26 was a miss because 26 wasn't there. But then 22 and 26 are hits because they're now in the cache. So then we go to 16, which is our 5th value. 16, the 2 least significant bits of 16 are 0, 0. So we look in the index. We see that neither set contains anything. So that would be a miss. We load it in. So that tag becomes 1, 1, 0. The tag is just associating the difference between the index and the value, the memory address. So we go with 3. The 2 least significant bits of 3 are 1, 1, right? So we then check 1, 1. We have a miss. They're in neither set. So then we load 3 in here. And then so then 18 is 1, 0. So this is where it gets tricky. So we have both of our sets have a 1, 0, right? So we have a 22 here and 26 here. Which one do you think we should swap out? I'll give you a hint. Think about locality. Items that are...
It would be 26.
Why 26?
Because it was the one that was most recently used.
Okay, so if it's most recently used, would I want to swap it out considering locality? If it's something that's been used,
If it's been
it tends to be referenced again. So do I want the most recently used or do I want the least recently used? You're on the right path. Yeah, we want the least recently used. So we swap out the 22. And MIPS does in fact, for those of you who've taken operating systems, MIPS does in fact be the least recently used algorithm for that. So just find the least recently used, swap it out. Let me scroll up a little bit so you can see the solution here. So the steps, 22 was a miss, 26 was a miss, then 22 and 26 were hits. So now we have 22 and 26 loaded in. 16 was a miss, so we loaded it into 0, 0. 3 was a miss, so we loaded it into 1, 1. 16 is a hit, we check it again. 18 is a miss, overwrite 22 due to least recently used.
So if you had, so instead of, so if you had 22, 26, 22, 26, 16, 3, 16, and you had 22 again, when you go to 18, would it overwrite the 26?
Correct. That's a very good question. So basically the question was, if we had another 22 access before that last 18, which one would we use? And we would pick 26 because that was the least recently used. That's correct. So you have a question or?
No.
Oh no, I'm just making sure because I'm going to be moving on here to that type of question you'd see on an exam.
So is the index, we always pick the two least significant
Yeah.
ones, or-
In this case, you pick.
or is that
So
just
here's
this case?
yeah. So what you would do to break it down is you would set with you got 2 sets, right? And then if you have 8, so in this case you'd have 8 blocks. Actually, the next question is actually going to be a very good description of the answer to your question. So I've had 8. If they're direct, they're all on the same street, right? For the analogy. And then I break it into, if I have a 2-way set, I have the 8 blocks, I break it into 2, 4. And then the index corresponds to, since I have, each one has 4 in it, I need 2 bits to count from 0 to 3. And so the next question actually will test your knowledge of that. So now I have example 5.8. Given a cache hierarchy with 8 words and a cache access time of 5 nanoseconds, so now we're calculating performance, and a memory access time of 20 nanoseconds. So this means if I have a cache hit, it's going to take me 5 nanoseconds. But if I need to go to perform a swap in the memory, it's going to take me 20 nanoseconds. And now we have the following set of memory accesses. A, if the cache is a direct map cache, show the sequence for accessing the cache and calculate the total time. B, if the cache is a 2-way set associative cache, show the sequence for accessing the cache and calculate the total time. Calculate the improvement in performance over the direct map cache in part A. This is a really good combining concepts type of question. So that means you would draw out this table. You would tell me in part A, you would say, all right, well, if I have 8 and it's directly mapped cache, I need to know that I can calculate the index. If you can draw out that it's 8, it means you know how to calculate the size of the index. You know, you can draw out the size of the tag. And so with these elements, I'm going to scroll up to the top here because I describe in detail each and every step. So this is an example of what I've seen students do in the past. Every student has their own way, as long as you get to the right answer. So you look at 1, 1, 0. The initial one's going to be a miss. It's not there. We look at 1, 0, 0. Nothing there. It's a miss. 1, 1, 1. Again, it's a miss. Now we look to 22 again because it's going to be 1, 0, 0. It's a hit. 16 is going to have 0, 0, 0. The valid bit would be no. We'd load it in there. So it's a miss. 13 is 1, 0, 1, so we don't have anything in there yet. So we change the valid bit to yes, load it in. That's another miss. 31, we previously had it there, so we would check valid bit 1, 1. It's there. so that's a hit. 8 is a miss because 0, 0, 0. But since it's direct map, that's the reason it's a miss is because we had 16 in there. So it's 1, 0, 0, 0, 0. So we had to swap out 8 and so we had to swap out 16 and put in 8. 5 is a miss. If we look at 5, 1, 0, 1, that matches to earlier to 13, right? So we would replace 5, overwrite 13, 13, overwrite 5, 8 is a hit, and then 5 is going to overwrite 13. For those of you who have taken operating systems, if I had a direct map cache and I had to go back and forth between 5 and 13, what is that called? What is that specific issue? It's an actual problem in operating systems. Thrashing. That's correct. So what the definition of thrashing is an instance where you're spending more time swapping memory than you're actually performing computation. So as you can see, one of the advantages of having a two-way set associative is instead of having to switch back and forth between this 5 and 13 over and over again, you would just have them both in there, and then each instance would be a hit. So the way to calculate the actual time is just to say, well, the misses were 20 nanoseconds, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9 misses, right? 9 times 20 is what, 180? This is this part. And then we go to the number of hits. So we have 22 is a hit, 31 is a hit, and 8 is a hit. So we have 3 hits, right? So each one of those is 5 nanoseconds. So the access time becomes 9 misses and 3 hits. So it's 3 times 5 plus 9 times 20 equals 195 nanoseconds. So for sequence B, by taking care of this, by splitting it up into set associativity, you draw out the index, which would be 2 here. So it's 8 divided by 2 becomes 4, and then that becomes your new index. So you need 3 bits. So we have 22 is a miss, 28 is a miss, so we load 22 in the first set. 28 is a miss, so we load 28 in the first set. 31's a miss, so we load 111 there, load it in. 22 is a hit because we had it in there. 16 is a miss, so we load it into the first set. 13 is a miss. Now 31's a hit. Now 8 is a miss. Now we need to overwrite 28 because we look at 8, right? So we had 0, 0, 0, we had 0, 0, 0. If we have in 28, it's set associativity, 8 is 0, 0, 16 is 0, 0, and 28 is 0, 0. So we loaded in 28 and then 16. And since 28 was the least recently used, we were able to do that. So we take the least recently used and swap it out. Then 5 is a miss. And then here's where we get the advantage. 13 is a hit, 8 was a hit previously, and 5's a hit here. Before we had to swap these 13 and 5 out, right, in the direct map. So the result is, instead of having just 3 hits, we now have 5 hits, which means we have 2 fewer misses. So now with just 5 times 5 nanoseconds plus 7 times 20 nanoseconds becomes 165. So the improvement in performance is execution time old over execution time new, which becomes 195 nanoseconds divided by 165, which becomes 1.18. Does everything about this make sense? People still scribbling. That's.
Why is the tag 3 bits in the 2? Yeah.
Well, the tag is just the difference between, it's just the address, right? So the full address, if we're going back to, is 8120, right? So I still need, if I have two streets, I still need to indicate where it is coming from in the higher level of memory. So in 32, if we have a 32-bit, if we have 32 words in memory, we need 5 bits to represent it. So in this initial value, in direct map, we figure out our tag because we have 8 blocks in the lower level cache. So we need 3 bits to represent it, and then the other 2 bits, going back to the equation, remember it's memory divided by block size? That's the same thing as subtracting. So think of it as subtracting. So we have 5 bits to represent all our higher level memory, and we need 3 bits to represent the lower level cache, so we have 2 left. And so that's the size of the tag. The reason why the set tag is 3 in the set associative, correct, because we have 2, exactly right, because we have 2 bits, I'll explain for the rest of the class. We have 2 bits to represent the index here, and then we need 3 bits to represent which one is which. Because the 3 bits allow us to represent figure out whether or not it's a cache hit or a cache miss. That's the information we need. Or to extend the analogy further, we are actually at the right house or at the wrong house. Party! No, it's not. Go away. Your tag is too short. Does this make sense? Let's bring some stuff back from section 1. Yep, good old speed up.
Good old days.
Good old days. Okay, so this is the end of section 5. So now we're going to go to section 6. So now we're going to put everything together. We have some fundamentals of memory. We've built an arithmetic logic unit. We understand instruction memory. We understand data memory. We understand the concept of a controller. We understand the concept of branch addressing, pseudo-direct, PC relative addressing, all that stuff. And we know how the instructions work. We know what an opcode is. We know how to access the registers. We have 5 bits and we decode it to go into the memory. We know it's at dual read, single write SRAM. So we have all these pieces which you'll put together in your first VHDL assignment, and then your project is just to put them all together. So TGOs 20.30, 20, 24, and 26 were the references in section 1 to the MIPS paper where I was talking about MIPS is compiler-driven encoding in the microengine. What's the basic philosophy of MIPS? What's the purpose of MIPS? Talking about the purpose of the data of the load store architecture. Hopefully this makes a lot more sense now as to why we would need a load store architecture. Because the whole idea is we only want to perform loads and stores when we absolutely need them, because any load or store operation, we have to go to the memory hierarchy, which means we might have cache hits or cache misses, which means it might take a long time. So we want to take advantage of this principle of locality, the spatial locality and temporal locality, put the things we're going to use most often in these fast local registers, and use these as much as possible. And then only store them back into the data memory when we're done with the variable, or when we absolutely need to perform a swap, which is done a lot of the compiler level. Since 1.24 it is a compiler-driven encoding of the microengine. So let's actually design this thing. Let's build a computer. Now you'll now say I actually built a computer. So first things, remember, what were the 5 stages of MIPS? Anyone already remember now?
Instruction fetch.
Instruction fetch, I'm sorry, that should say that's 1.20. Instruction fetch. So I now have my 32-bit instruction. It's all binary values. So if I want to figure out what that means, what do I have to do to these? No, that's the 3rd stage. ALU is 3rd stage. So what's the 2nd stage?
Instruction code.
Decode. I need to decode those values. What's the 3rd stage? ALU, right? So now I've decoded it. I've got the information from the registers. I actually put this value into the ALU and it performs some operation. What's the fourth stage? Yep, you guys are both on the right track. Data memory. Okay, so the whole idea is we then check in this fourth stage whether or not we actually need to access the memory hierarchy. And the fifth stage, someone besides Lee? Store the result in the registers. And what is the actual term for that?
The instruction memory?
No, instruction memory is the. After you see the data path, the term for it will make a lot more sense. It's called write back. Because we're going to be going instruction memory, decode, registers, put that information in the ALU, then we check the data memory, and we're going to use a multiplexer, and it's going to go back to the registers. So it's going to be write back. Instruction fetch, instruction decode, execute, memory, and write back. So the instruction fetch stage, we're going to consist of a program counter, which, as you recall from memory addressing, contains the memory address. So in your section 4, you're going to be loading in those values from program.txt, right, as you recall? And you'll start at 0, and then you increment every 4. Now, why do we do the PC plus 4? Byte addressing, exactly right. So the stage is, this one's simple. Program counter, we have a value, goes into the instruction memory. We have the read address, we take that PC, we have an adder here. So we show it in the problem how you're going to do that different in your VHDL assignment. But in this case, we have a 32-bit value, and this should be 100 with sign extended to 32 bits. And then you have an output. Now, unfortunately, it's not going to be as simple as this because we have to calculate branch and jump addresses. But this is just the first stage. So now we have our 32-bit value out here. So the second stage is instruction decode. So now we have, it's either an R-type, an I-type, or a J-type instruction, right? Good, what? So now we have 32 bits. So what were the 6 most significant bits of the instruction? Opcode, right? So the opcode, after emerging from instruction memory, is going to go to the controller. What are the next 5 bits, 25 to 21? RS, right? So 20 to 16, this is where it gets a little tricky, right? 20, yeah, so in R-type, it's to RT and RD is 20 to 16 and 15 to 11, right? Mm-hmm. But what is 15 to 0 in an I-type instruction?
Is it immediate?
It is the immediate value. So we need some sort of we need something to differentiate between that 15 to 11 if it's on R-type, because we don't want to put a 15 to 11 into to give me that value if it's just going to be something that it's just a immediate value, because now we're getting wrong. We could be getting wrong values out of the registers. So if I had to decide between 2 5-bit values with a control signal, what would I do? What logic structure would I use? I had 2 5-bit inputs, and I wanted 1 5-bit output on the other side. What would I want to design? A multiplexer. Very good. So we're going to use a multiplexer to differentiate between the 20 to 16 and 15 to 11. Because in the I-type instruction, you can often use the 15. Remember in add I, we're using that 20 to 16 to determine where we want to write to. Whereas in a branch, which is also an I-type instruction, we'd be going to RS and RT to get the 2 values out to compare them in the ALU. So we need that multiplexer and the control signal to determine which one is which. So that we have those 2 control signals. We're going to use register write, which is used to indicate if a register is being written to or not. If 1, then the register is being written to, and if 0, no register is being written to. This means if it's true, write. If it's not, don't write. Pretty straightforward. And this third one and this is basically just a description of everything I was just talking about. This third one here, register destination, is used to determine if RT or RD register is being directed to the right register. It controls a multiplexer. If it's 0, then it's going to be an I-type, and you're going to take 20 to 16. If it's 1, then it's an R-type instruction, and it's going to send 15 and 11. Make sense? So now you can see how the controller is actually going to be, you're going to be using a truth table logic to figure all of these different control signals, right? Wait, there it is, okay. I thought I got lost there for a second. Okay, so the control signal, so this here is talking about what we're doing with 15 to 11. So I'm at 15 to 0. So what we're going to happen is we're now going to take that 15 to 11, but we're also going to fan out, and 15 to 0 is going to circumvent the registers entirely. Now, if you remember from the integer addressing, the immediate addressing, we actually have to take that 16-bit value and we're putting it into the ALU, correct? So we have to sign extend it by 16 bits to make it a 32-bit value. So, but in your data path, it's going to be different because you're only going to want 8 bits of that value anyway. You're going to get 32-bit address coming out, and you're only going to want the 8 least significant bits, so you're not going to do any sign extensions. But on the exam, when I ask you this question, you will put it in. Does that make sense? On an exam, I want the full 32 bits. Now, we've already talked about the ALU WAP, which is TGOs 6.4. Let me scroll up a little bit past 6.2. Is a 2-bit control signal. So it's coming from the controller, and it's going to go to this ALU controller. Now, what are the 2 inputs to the ALU controller? The 2-bit ALU WAP, and what's the other thing? How do I differentiate between R-type instructions? Remember, R-type instructions all have the same opcode? So I have the opcode, RSRTRD. We have a shift amount. And what's that last 6 bit? What are those last 6 bits called? The function, right? So the 2 inputs to the ALU WAP are the 6-bit function and 2-bit control signal. And we use that to determine which would remember we have a 16 to 1 mux to multiplex every value on the output of the ALU, right? So we need to have a 4-bit value coming from the ALU controller going straight to the ALU. And so give everybody a split second to write down the ALU WAP. Now can you see how before I show you the actual drawing, you see how these pieces are starting to come together a little bit? And all the things you've been doing in the past at C. Yes?
When you said this stuff will be on the test, you're talking about exam 3, right?
Yes. No, exam 2 was, the end of exam 2 was last Thursday. When we did the review that I posted on the video, the exam will be some subset of that. Nothing that we're covering today is going to be on the exam. That's also why I said at the beginning of the lecture that this homework assignment will not be due until next Tuesday. Because I don't want you doing this assignment. I want you focusing on studying for your exam. Does that make sense? Yeah, no, this is all on the final. Okay, so this is the drawing of the instruction decode stage. So we get the instruction memory out. The opcode goes to the controller. 25 to 21 goes to read register 1. That's RS. Where we have the 5-bit goes to the 5 to 32 decoder, gives me the value, and then reads it out. So these output values are 32 bits. 20 to 16 always goes to read register 2. And then if we add I, we'd have a 0 because it's an I-type instruction. If it's a 1, we want the right register, the value we're going to be updating at the end of the instruction, to be 15 to 11. 1 is going to be an R-type instruction. 0 will be an I-type instruction. So to give you a hint, this is where the write back comes from. because this will be coming, we'll have the data memory and then a multiplexer out here, and then this will come back. So write data, this 32-bit value, this is the address I want to write to, and this 32-bit value is the actual value we're going to be using to update it. So if you recall from the previous lecture, we had that 32-bit write input, and then and we had this specifically, it would read the data out on the positive edge, and we had the program counter at the negative edge. The reason why we did it at the negative edge is so that way, while we're getting this address here, we can update the previous instruction immediately. So then we hit the positive edge, then we write out. That's how we get this write, then that's how we physically obtain this write then read capability in MIPS. And that's why it's important. So you get that information back so you can have the most recently used copy of the variable to perform the correct operation. So here we take the 15 to 0. So that's the immediate value. We sign extend it. It's going to be 32 bits. And then the ALU stage, we're going to be doing stuff with it for the time being. It just comes out here. And then we take the 5 to 0, which is our function, as we described earlier, and we send it to the ALU control. This ALU op is a 2-bit input, and this is going to be our 4-bit output, which we'll describe in the next stage. Does anybody have any questions about how this is working so far? Yes.
What about the shift? Like we just went.
Okay. Well, yeah, we'll address that at the end of the data path. But yeah, this would come from the 10 to 6, and this would come along and go into the ALU. I should note that one of the reasons why I do it this way, in the textbook, it doesn't actually have the shift value going into the ALU. In the diagram, they kind of left that out. So in the final data path, let me scroll down here for a minute. In the final data path, I do account for it. So this is the 10 to 6 here. But let's not jump too far ahead. So here we are right here. Don't want to scare it. I think you guys can handle it at this point. You know all the pieces. So now we have these read data 1 value coming out here, and we have this read data 2 coming out, right? So, but I also have this sign extended value, right? Coming out here. And I need to decide, so if I was an R-type instruction, both of these values would be going into the ALU. If it's a add immediate or a load word or a store word, this value, this physical value here, the sign extended, that is our offset. Read data 1 is going to contain our base address. And read data 2, as we'll show later, is going to contain the actual address we're going to be going to in the data memory, which we'll show you in that 4th stage. But the read data 1 plus the sign extended value, that's either going to be our add immediate or load word or store word. So we need to make some 64 to 32 comparison. What would I want to put there? I'm trying to have 64 bits. So I have a 32-bit value coming from read data 2. I have a 32-bit value here. And I want only one of them to go to the ALU. So I only want one 32-bit value. What would I use? Yeah, you'd use this. Yeah. So you have this, okay, so it would be a 64 to 32 multiplexer, but you're correct. So it's 2 to 1. And you guys have already built that, right? So you would have, since it's going to be the second source to the ALU, the control signal that's going to control that multiplexer is called ALU source. And that ALU source is used to differentiate between read data 2 and the sign extended instruction as the source for the second ALU input. The ALU also receives the 4-bit output from the ALU control. So this here is going to be a 4-bit value that, if you recall from the previous TGO in Chapter 3, you actually know how some of those values control and, or, add, subtract, set less than, and then you can actually take these values. In the later TGO in this chapter, which we'll cover next week, we'll actually get into how that's actually physically done in the ALU control. So the 32-bit sign extended address. After this, remember from base addressing and pseudo-relative addressing, we actually have to do the sign extension by 2 bits. So what's going to happen is this value is going to be multiplexed, and that's going to fan out and go here. And we have to shift left by 2. And why do we have to do that? What's the 2-word term? If I have to shift left by 2 for something, what? Because I'm multiplying by 4, because it's a 2-word. Somebody actually said it earlier when I asked before. Think, what do we just do in Chapter 5? And what type of addressing does MIPS have? Bingo, we have to do byte addressing. So we're going to be shifting this value by 2 after it fans out to the multiplexer. And then we're going to add it to the output from the PC plus 4, because now that tells us how many values we're going to branch. So if you recall, when we were doing this hopefully will help you understand why when you do a branch, remember if you're branching past 5, the value that's going to be in the immediate is 4, because it would just normally go to the next instruction, but then you have to branch past 4. The reason why physically it would be 4 instead of 5 is because we've already done PC plus 4 in the Datapath just to get to that next instruction. Well, I want to go 4 more to get to that other instruction, right? So that's why it's going to be 4 instead of 5. Does that make sense? Yes, no? Nobody's answering.
Can you say it one more time?
Okay, so if I want to branch past 5 instructions, right? And I have an immediate value telling me how many instructions I want to branch past. And you think to put in 5, but I told you when we were covering that it should actually be 4 because we physically have already gone 1 further. The reason why is because we go back to the instruction fetch stage. The first thing we do is we increment by 4. For using byte addressing, we've already incremented by 1.
Is that why whenever we did as on the last quiz we did was with the 256?
Yes.
280?
Bingo.
Is that why
So it's 256. If you're a branch exactly. So if we're branch instructions at 256 and we want to get to 260, we normally have to add 4, right? Because, but the thing is, since we've already physically had PC plus 4 in there, no matter before it actually gets to the branch instruction, it's already at 257. So then we just add 3 to get to 260. Does that make sense? So that's what's physically going on. That's why you have to do it that way. And so we will conclude lecture today with the instruction decode draw up. So here we have this is our PC plus 4, and this is the PC plus 4 is here. So we have our sign extended value, right? It's multiplexed with the ALU source and read data 2, as we indicated in the TGOs previously. And it's multiplexed. Read data 1 always goes to the ALU. So this 4-bit ALU op is actually coming from down here. It's the output of the ALU controller. And then we take the sign extended value and we're shift left by 2 and then add to the PC plus 4. Now we're going to fan out here. So we have this would be if we're just doing the next instruction, and this is where we'd branch. So next week, next Tuesday, we're going to be talking about how we take this 0-bit and calculate whether or not we want to branch. Because we would calculate a branch every single time, and we could say, yes, this is a potential branch. We could create the branch control signal. but we also have a condition. It's branch on equal, branch not equal, correct? So we need to determine whether or not they are equal or not. So if you recall, I told you to put a specific output for the comparator that indicates whether or not they're equal. You're going to use that output from the ALU to go to an AND gate where you have branch and that signal to then determine whether or not you're going to branch or not. So you're going to put that all together. So the homework due next Tuesday, and it's 6.1 through 6.7. And then section 5, we did .13 through 5.17. And then example questions 5 through 8. Okay, in that case, you're dismissed.